So previously, we have discussed how to find velocity from position. That's the problem of differentiation. Now we're ready to discuss the opposite problem, namely recovering position from velocity. This is, in a sense, the problem of integration. But first, before delving deeper into integration, let us quickly recap what we've got so far and clarify and review our terminologies and setup. We have a position function as t, which takes in as input some time t and output your position at the time t. More precisely, s of t tells you how many miles up north you are along State Street at time t. If you know the function f, i.e. if you know your exact location at every point in time during your run, then you could also figure out your velocity at every point in time during your run in the following way. To find your velocity at any time t, say t equals to 7 a.m., you would first compute your average velocity over some time interval delta. This is obtained by dividing the distance traveled by the duration traveled, which is delta. Now, you find the distance traveled by subtracting your position at 7 a.m. from your position delta hours later, which is just s of 7 plus delta. This tells you how fast you were running on average within delta hours of 7. Now, to know your velocity right at 7, you just take the limit of this average velocity as the duration delta approaches 0. i.e. you want to take your average speed over smaller and smaller time interval around 7. Now, another name for this limit is the derivative of s at 7. It's the slope of the tangent line to the graph of position right at the time 7. Now, of course, there is nothing special or magical about the number 7. You can definitely apply the same argument to find your velocity at any time t. That's just gonna be the derivative of the position function s at t. Alright, so we see that to get velocity from position, we can simply differentiate. How about going in the other direction? Suppose you know your instantaneous velocity at every point during the run. Say, for example, you have some type of running speedometer. I don't know, but maybe Apple Watch or Fitbit? Maybe they do that. Now, with that data, would you be able to recover your position at every point in time? Would you be able to tell exactly where you are, for example, and say 7 a.m.? What do you think? Would you? Well, let's try. So, let's suppose that you were able to maintain a constant speed of 5 miles per hour throughout this run. That means that at every moment throughout this run, your instantaneous velocity is always equal to 4 miles per hour. You never slow down or sped up. Could you then tell me, where exactly are you at 7 a.m.? You were running on State Street, right? So exactly at which point on State Street will you be at 7 a.m.? Now, do you see what the issue is? Remember, Adonis pointed this out to us in class last week. Your position at 7, at 9, at 11, at any time, they all depend on where your starting position is. Well, if you started running at 5 a.m., then by 7 a.m., the total distance you have traveled, i.e. your so-called total displacement, will be your velocity times the duration travel, which is 4 times 2, and that gives 8 miles. So you know that if you started running from 5, then by 7 you would have traveled 8 miles. But that does not tell you your location because you don't know where you started. You don't know where you were at 5 a.m. If you were at 0 north at 5 a.m., then that means by 7 a.m. you would be at 8 miles up north. But if instead at 5 a.m. you were at 800 north, then by 7 a.m. you would be at 808 north. So you see, velocity does not determine position uniquely. This is secretly why, when we take the indefinite integral of a function, we don't get just a single function. Instead, we get a whole family of functions differing by some constants. Do you see it? Well, if not, don't worry. We are gonna explain this now, okay? Now, let's check to see if you truly understand what we were talking about. With the same setup, could you tell me, in plain English, what does the indefinite integral of your velocity function tells us? Now, some of you will say that it gives us your position, or more precisely, your position function. But that's not quite right. It gives you all possible position functions, not necessarily your position functions. So let's see why, and again review the difference between an antiderivative and the indefinite integral. Now observe that your particular position function is all but one possible antiderivative of your velocity. Recall that an antiderivative function of the velocity function is any function whose derivative is equal to the velocity function. Your position function is one such function, but there are infinitely many other ones. Actually, the position function of any other runner who runs with exactly the same velocity as yours will be an antiderivative of v. Right? You see, if ft is the position function of some guy, say Frank, at time t, and you know that the velocity of Frank is given by the function vt, then you know that f prime of t must be equal to vt, and so ft must be an antiderivative of vt. So the antiderivatives of vt are exactly the position function of all the people who run with exactly the same velocity as you did. At any time t, you're all running with velocity t. So that's what the antiderivative of vt means in this case. And then the indefinite integral of vt gives us the totality of all possible antiderivatives, i.e. it gives us the position function of all the runners who were running with exactly the same velocity as yours. And it turns out that the position function of all of these runners are all gonna just differ from yours by some constant. The constant is here to account for the difference in the starting point between you guys. So let us look at a concrete example to see what this means, okay? Let us say that the starting point of your run is 800 north. Now let's consider another runner with the same velocity. Let's say you have a stalker with very good eyesight, and at the same time when you started your run at 800 north, the stalker started running at 0 north. If you guys are running with the same velocity, then tell me, by the time that you arrive at 1200 north, where would the stalker be? Well, let's look at it together. Right at the beginning, the distance between you and the stalker is 800 miles. If he's good enough with keeping exactly the same velocity as yours, then as you two run, your distance will stay constant. It's always 800 miles. So by the time you are at 1200 north, he should be at 400 north. If you know Galilean physics, you know that motion is relative. So if you and him are running with exactly the same velocity, then you guys are actually standing still relative to each other. So your distance is always constant. It's always 800 miles. Thus, more generally, when you are at position st, where would he be? Well, he would just be at st minus 800. So you see, if any runner runs with exactly the same velocity as yours, then the distance between you and him is constant. It's equal to the distance between your starting points. And so, if we call this distance c, then his position at any time t is just going to be exactly equal to your position minus c. Well, minus if he runs after you and plus if he runs before you. But plus or minus, that doesn't matter. The moral here is, two people run with exactly the same velocity if and only if their position functions differ by a constant. This constant is exactly the distance between their starting point. Thus, if you were running with velocity function v and position function s, then all the antiderivative of v must be of the form s plus some constant. That is just another way of saying that the position function of all the other runners with the same velocity function must be the same as yours plus a constant. In the next video, we're gonna give another way of seeing this in terms of graph, which will then help us introduce definite integral and build up to the fundamental theorems of calculus.